Hello everyone, welcome to my talk. My name is Hyoung and going to present you about LSM-Trees under memory pressure. This work is a collaboration with Zichen, Aneesh, and our advisor Manos. The log structure merge tree is a key value store that is widely adopted in many database systems, such as VLDB, LevelDB, and many more, because they balance the read and ingestion performance. To support fast writes, LSM-Trees store all inserts in a memory buffer. When the buffer is full, it flushes the buffer to storage as an immutable sorted one. In order to balance the read performance and ingestion rate, LSM-Trees maintain these sorted ones in multiple levels. Depending on the compaction policy, there can be only one lump level or multiple ones, but the size of each level grows exponentially by size ratio. Oftentimes, ones are organized in SSD files so that a small part of the level can be compacted. To enhance the lookup performance, the commercial systems employ metadata such as Bloom filters and indexes. Bloom filter can identify whether the target key belongs to a given level or not, so it can screen out the keys that have no possibility of matching. Indexes are the min-max ranges for each disk page, and they ensure that at most one I/O occurs within a single one. A point lookup first checks the in-memory buffer and then traverses the tree from the shallowest to the deepest level until it finds the first match. In order to keep useful blocks in the memory, LSM engines often use block cache. For each level, Bloom filter is always looked at first. If it is not in the cache already, it has to be fetched from the storage. Then if the Bloom filter query result is negative, then the lookup moves to the next level. For the next level, Bloom filter is looked up first. Since it is not in the cache, the filter block needs to be fetched from the storage. Then Bloom filter is queried. For a positive result, the lookup needs to access index to find out the data page that the given key belongs to. Similarly, index block needs to be fetched if it is not in the block cache. Searching index returns the position of the data page that contains the target key. Then lookup tries to access the first data block as index indicated. Since it is not in the cache, data block is fetched from the storage and search for target key. Finally, it finds the matching key and lookup finishes. When the new query comes, IOs to fetch indexes or filters can be saved because block cache caches useful blocks already. The lookup starts from the first filter of the first level. Since it is in the cache already, we can search it with no extra IO. Due to the negative result, the lookup proceeds to the second level. Again, the filter block is in the cache, so we can search it with any extra IOs. Due to the positive result, the index is searched to, which is already in the block cache. Now, a lookup accesses the data block. Upon this, the data block is need to be fetched. Then we can find match. So the lookup finishes. As shown, the block cache stores the frequently accessed blocks, thus can save the IOs fetching filters, indexes, or data. However, can we always keep useful blocks in the block cache? Let's look at the memory pressure in LSM-Trees. This table shows the history of memory and storage technology. The price drop in memory has been slower than storage, and this makes it hard to maintain the same memory to data ratio. Further, data keeps increasing. Thus, the size of metadata also grows. As the size of the data grows, the file size also increases to avoid frequent compaction that makes the size of each block bigger, which makes it fine-grained control harder. On top of all this, the memory to data ratio is decreasing. So now we are facing the memory pressure. Moreover, LSM-Trees uses memory for a number of different components. The block cache to enhance the lookup performance, the in-memory buffer to store incoming data, temporary memory to compact the data, and to support ongoing range queries. Let's look at what happens when there is a memory pressure. This figure shows the lookup performance on the various memory budgets. As the available memory decreases, the read bytes per query increase rapidly from 12 kilobyte to over 270 kilobyte, which is a 23 times increase. In order to improve the lookup performance under memory pressure, we focus on the filter blocks. The state-of-the-art LSM designs treats all balloon filters equally, having a uniform memory allocation policy across all balloon filters. However, are all filter blocks equally important? This figure shows the access frequency of SST files during lookups. Even in the perfectly uniform workloads, 80% of the lookups are directed to only about 45% of the SST files. If your workload is skewed, even fewer SST files are accessed. We have larger files. The size of balloon filter per SST files also increases. That occupies several pages. But similar to the fact that not all SST files are equally useful, not all balloon filters are equally useful. So can we load fewer bits from non-useful balloon filters? In order to achieve that, we propose a new design. But before describing our new design, let's take a detour on textbook balloon filter to set the stage. Balloon filter is a simple bit vector that can identify the membership of inputs. To query a balloon filter, we need to calculate k-hash indexes and serially check the bits indicated by those hash indexes. If all bits are set, then it is positive. Here, we always need to access all k-hash indexes for positive queries. If there are any bits with value 0, then it is negative. For negative result, balloon filter can screen out the unnecessary data accesses. However, is the entire filter useful? In order to find out, let's look at the average number of filter probes for empty queries. We need to check the filter at least once. And with probability of 1/2, we need to check the second bit. This goes until all k-hash indexes. Thus, the average number of filter probes for empty lookups would be less than 2. In order to utilize this characteristic, we propose modular balloon filter. Modular balloon filter consists of multiple modules, and each module is also a balloon filter with smaller size. The lookup on modular balloon filter is also sequentially done by modules. Whenever modules returns the negative result, the query ends. Thus, it can reduce the number of module accesses. If all modules return positive, then the query result is positive. We conducted a benchmark to see the first positive rate of the modular balloon filter. As we can see, modular balloon filter shows the first positive rate that is close to the theoretical expectation. Next, we compare the average number of module accesses for various number of modules. The number of module accesses grows as there are more modules. However, size of each module decreases as there are more modules. Thus, there are less space requirements when there are more modules. Let's move back to the positive case. Modular Bloom filter can reduce the average space requirement for empty lookups, but still we need to access all modules for positive cases. What if we know something more about the queries? Here we propose skipping modules when there is no benefit. In order to quantify the benefit of using filters, we introduced a new metric, utility. Utility is the number of IOs that can be saved by using a module. This is the formula for the expected number of IOs. IOs occurs when there is a positive result from a Bloom filter. It can be either true or false. And access frequency of the SST file also matters. Thus, utility is high when the file is highly accessed or queries are empty. This is how our skipping algorithm works. Before accessing which module, we need to calculate its utility. When there is no benefit, we can skip querying the modules. When there is benefit, we keep querying the modules. Using our modular Bloom filter with the skipping algorithm, we can vary the bits per element for filter based on the benefit. Thus, our proposed design can navigate the trade-off between memory and performance. We combined our proposed modular Bloom filter and skipping algorithm with a hash sharing technique to minimize the hashing overhead maintaining multiple Bloom filters. And we implemented in the state-of-the-art LSM tree and proposed a novel LSM design called Shamba. From now on, I am going to show you the experimental result of Shamba. We compare the performance of Shamba to our in-house LSM tree prototype based on the state-of-the-art LSM design. The left table shows the LSM tuning parameters we used, entry size of 64 bytes and key size of 32 bytes. We set BMP to minimize the size of data block. 10 bits per element is used for Bloom filter. Right-hand table shows the resulting block sizes. To minimize the data retrieval cost, size of data block is 4 kilobyte and size of index is 32 kilobyte, and resulting filter block is 80 kilobyte. There are 3 tuning knobs of Shamba: the number of modules in the modular Bloom filter, the size of each module are equal or the proportional to the memory budget, and the skipping algorithm, non-partial or full. We compare these variants of Shamba. First, either equal sized or proportional to the memory budget, whether there is no skipping algorithm or a partial skipping algorithm that allows to skip only the part of the modules, or full skipping algorithm that can skip the entire filter if there is no benefit. First, we evaluate the impact of the number of modules. Here, no skipping algorithm is used, and we vary the memory budget from 10% to 150%. As we can predict, the performance improvement for modular Bloom filter is bigger for empty queries. As the non-empty ratio increases, the benefit also decreases. Also, we observed that Shamba performs best with smaller modules. This figure shows the ratio of queries terminated for various number of modules. When there is only one module, the entire filter is needed. When there are 2 modules, about 90% of queries are done by using only half of the filter. As the number of modules grows, the more queries can be finished by using only the fraction of the filter. So the smaller modules are more beneficial. Now we applied full skipping algorithm to the previous experiment. Here, the performance improvement is not affected even for all non-empty workload, since skipping modules aggressively reduces the impact of the number of modules. However, when there is a memory budget more than we need, the performance of Shamba is worse than the state of the art. This is because skipping algorithm uses the same threshold value for all memory budgets. We believe this can be improved by changing the threshold value accordingly to memory budgets. In this experiment, we implemented Shamba into partitioned index and filter. Partitioned index and filter is introduced for memory pressure. Thus here, we further reduces the memory budget from 5% to 35%. As shown in this experiment, Shamba boosts the performance of partitioned and index filter under severe memory pressure. We also consider Monkey. Monkey allocates more bits per element in the shallow levels to reduce their first positive to achieve fewer overall IOs per lookup. Since the first few levels have larger bloom filter, we find Monkey is a very good candidate for our modular bloom filter. This experiment shows the Shamba further improves the performance of Monkey. From now on, we are going to show you the query latency of Shamba implemented in real system RocksDB. First case is when there are two equal sized modules. As shown, Shamba accelerates point lookups in the real system. The second case is when there are two modules with different sizes. We set the size of the first module proportional to the memory budget. For example, when there is a 10% of memory budget, the size of the first module is 10% of the entire filter. When there is 70% of the memory budget, the size of the first module is set to 70% of the filter. When the available memory is larger than necessary, only one bloom filter with full size is used. As shown, the performance improvement is little less than the equal sized modules, but proportional sized modules also accelerates point lookups. We also evaluate Shamba on various storage devices, SATA SSD, PCIe SSD, and RAM disk. As shown, Shamba also benefits faster storage devices. Lastly, we evaluate the performance of Shamba with larger index. In order to increase the size of index, we increase the entry size to 128 bytes. And we vary the key size from 8 bytes to 124 bytes. Left-hand side is when filter is larger than index, and as we increase the key size, the index becomes larger than filter. As the filter size grows, the speed up also increases. The Shamba is a great fit when filters are larger than indexes. To conclude, we have proposed a modular bloom filter, which consists of multiple modules, so that modular bloom filter enables smooth navigation of the trade-off between memory and performance. Using modular bloom filter, we propose a novel LSM-based key value engine, specifically addresses the performance loss due to the memory pressure. Our experimental results shows that with 1/3 of the memory budget, Shamba can achieve the same performance as the state of the art. Thank you very much for your attention, and I'm happy to take any questions.